Hello everyone, welcome back to the fourth video in the series of basic STK usage. So I want to talk about hierarchical construction, which has its own section in the latest STK paper. If we go to the bottom, we discuss it in short detail, like everything in the paper, about how all molecules are stk.molecules or classes of them. So we have an stk.molecule. A building block is a class of type molecule, and a constructed molecule is also, which means we can go from a constructed molecule to a building block and use that, whatever we've generated, as a building block for a new construction process. And so this allows us to, build up more and more complexity. And we show some examples. We talk about examples in the manuscript, like for metal cage construction, like we showed in the previous video. You might start by building the metal complex and then put that on a cage topology graph, or you could put that on a linear polymer graph and get a coordination polymer, for example. In the actual manuscript, we show an example which I will generate from scratch, the construction of a series of retaxanes from a class of macrocycles, caps, and linears. I have a paper that's being written up at the moment which does the same thing to generate a large library of potential cages. So I think this is very powerful, and this is why I wanted to show it. So what I want to show first is an example I used in a talk recently where I saw a collaborator of mine published a paper on a cool looking structure, giving a shout out to Jamie here. If we look at his latest papers, I always forget what the paper's called, so I got to find it. If we look for the paper, it is this one, self-assembly of a porous metallo-fiber retaxane. I'm not going to go into it, but basically it's a metal organic cage with retaxanes on the exahedral functionalization of the ligand. And I saw this and I was like, how do you generate this in STK? And can we do that? And I think we can with the retaxane and the cage classes. So I'm not going to write this one because this one took a little bit of time to do from scratch, but I'm going to show the code to generate this. And this is also available in STK examples under vmask retaxane cage. So this is our set of manually built building blocks. We have cycle BB1 and 2, so I'll just get them up in PyMol. Let's put it on grid mode. Cycle BB1 and 2. We have axle, cap, linker, and core as well. So let's go axle, cap, core, linker. So these are all of these are so small you could write a smile string probably by hand to generate them. Like these are trivial molecules in my opinion. And so what I'm showing here is that from this subset of 6 trivial molecules, we're going to build from scratch that retaxane cage. Cool. So the way the code works is first we have to generate the ligand. I've got an if statement here that says if it already exists, then don't rerun it from scratch. But I actually do want to rerun it from scratch to show how long it takes, and it takes about a minute, so it's not that long. But if we remove full ligand.mol, then we can run it from scratch in the background. While it's going, I'll run through what the code does. So it's running. Cool. So the first thing the code does is it builds the axle. So the axle of a retaxane, let's see if I can actually give myself the... I I would like to also show the chemical structure. So let's make this smaller. Let's open up this, put it down here. Cool. So, just for a reminder. So the axial of the retaxane looks like this. It's basically ligand 3. So we build that from axial BB and cap BB. So this is this molecule here. You can see we haven't optimized it. It's just left as is because I think that's simple enough, but it looks as we would expect. We've separated, so it's from axial and cap. So it's from this molecule and this molecule, and we just couple it through bromine groups. So we purposely put on bromine groups so that we could do this fake coupling. Cool. We then generate the macrocycle. So this is from the 2-cycle building blocks, which again also have this. They have the correct functionality. Well, correct is the wrong word, but what was actually used, and it's the carboxylic acid groups and amines. You can see we've defined those. So primary amino factories and carboxylic acid factories. Here we actually modified the deleters, and so they come together to give us the macrocycle. So it's called macrocycle. There we go. Cool. Again, unoptimized. And this is just so that we can do the threading easier, basically. We then thread the axial and the macrocycle together on a retaxane topology graph, which we can generate here. Cool. We can then optimize that with stk-tutorials, and it's RDKit UFF implementation, where this flag ensures that we can get the intermolecular interactions on. So we can then go to retaxane, and cool, that's a retaxane. It is, I mean, it's not perfectly optimized because it's UFF in RDKit, but it does the job. And you can see that we now have this iodine group at the end for doing the next coupling step. So we do that by, we can build the ligand from the core and linker BB. So I'll show that, core, linker, and we couple those together to form the ligand unoptimized. Looks like that. Now, we want this ligand to eventually look like this and have this kind of banana shape. And this is not going to be amenable to cage construction. So I wrote a function which I've just called direction here, and I'm not going to go into it. And it takes a little bit of time, but basically it generates, with RDKit, it generates like 100 conformers of this molecule, and then it finds the one that most resembles this, or most closely has the nitrogens pointing in the right direction. So that will be ligand.mol, which we write here. So if we go ligand, cool, so that's the output there. And so now we've got the ligand and it's connected by this iodo group. We can now use the polymer class to couple them together using iodo factories on, so in it from molecule, the retaxane and the ligand, using an iodo factory, and hopefully this gives us the full ligand .uo_uo. So if we go full ligand UO, so you can see it's coupled the retaxane to the ligand, and we perform an optimization on that, and it should look like so. Cool. So now we have this full ligand. Excellent. And that looks like this. Great. We can now perform normal cage assembly. So we generate a palladium atom with 4 functional groups, and using the Smart's functional group factory, we take this full ligand, give it the pyridal functional group, a dative reaction factory, optimize it with MC Hammer, and we should get cage C. And that looks, I mean, it's not perfect. Obviously, again, it requires further optimization, but it is a good initial guess for a lot of kind of property calculations you might want to do. Cool. So that code is available. I'm going to exit this now, exit this, and just show that so I used 40 conformers to do the directionality to get the full ligand, and that took 50 seconds, the whole thing, to generate the new cage. And I'll just show it again, cage c.mol, and you can see this was generated as we were doing that example. I mean, still not perfect. You can see the bend in the palladium center, which should be square planar, but I would argue that you could throw this into UFF with metal parameters, so not RDKit, which is available in STKO through the software Gulp, or you could throw this into GFN-XTB, also available through STKO, and get a reasonable structure pretty quickly. Cool. So let's go into the example I wanted to go through from the paper. Where is it? We want to recreate this process. So we want a series of macrocycles, a series of caps, a series of linear connectors, and all of that. Now I wonder if I can't copy that, so I'm going to have to write this down. But basically, we want macrocycles, caps, linear 1, linear 2. I'm back. Here's one I prepared earlier. This is actually the code I used to generate the figure for the paper. So we have, let's separate this. So this here generates, this here generates a macrocycle, but let's do that a bit more complicated. Cool. And then we have the definition of some caps and some building blocks, and this gives us that. And then we have the iteration, which I will show at the bottom. Cool. So we generate a macrocycle in a normal way, yep, that makes sense. We have the two building blocks, repeating unit, so forth. This orientations is just used to set configurational isomerism again, and cool. So we can generate a macrocycle. Oh, we need to import STK. Makes sense. Let's go show stk-mol macrocycle. Excellent. We can then generate all these building blocks. Let's, for example, look at the caps. Let's go CB3. So that cap, and then that you can see has only one functional group on it, whereas BB1, for example, has two. Cool. So what we're going to do is iterate through the product. So this is an itertools, like a combinatorial process. So we need to import that from itertools import. Oh, can't type. Product. So this will build a polymer with this repeating unit. So this puts the cap on either end, 2 of linear 1 surrounding 1 of linear 2. Repeats that once and generates an axle from that polymer. And then that axle is then placed in a rotaxane with the cycle which iterates over the macrocycle. Now if I run this, what do we think is going to happen? File not found. Okay, let's go and let's make this directory os.meta cool, so that should have run, and if we open up we can see a series of mol files. Excellent. So I will go back to pymol. Yep, where are we? Yeah, here. And go code. Excellent. And go pymol. Right, there we go. So let's show this as sticks, and you can see we have only one macro cycle, so they all have the same macro cycle, no changes there. But we can see the changes we've done with the polymer, where we've swapped out, if we, for example, go wrote hierarchical 0 versus wrote hierarchical 1, that swapped out the central building block. If we verse 0 to 2, that swapped out this kind of middle connecting building block, and so on and so forth. This one swapped out the cap, the middle, and the other building block, and all of these, I guess now we can use. So when I originally wrote this, we didn't have this code, but now we can do this. We can go optimizer equals stk dot mc hammer, and do the same for the macro cycle. Cool. That all might not be the best structure to build. Yes, I actually think that macro cycle is going to be not very good for this. So if we want to go target bond length is normally quite small, but if we make it bigger, then the macro cycle might not collapse as much. So you can see it's borderline good. Then hopefully, yep, that error exists. Cool. Hopefully this can now run. Yep. So it's having. Oh no, we don't want to optimize the rotaxane. That's silly. We want to optimize the polymer. Cool. Now that should optimize all of them. We go back to pymol. Once that's done, didn't take very long. Cool. So yeah, clearly this is not a great physical example because I haven't completely optimized the macro cycle, and I wouldn't expect that macro cycle to be big enough to actually fit the axle as is, but maybe if there's benzene rings rotated or something, it might work. But this is not the point. The point is that we can build, these structures which are reasonable from a physical point of view, and you would probably run some optimization, realize that they're really high energy, and throw them out in any screening process. Cool. Okay, so I'm going to stop this video here. Thank you very much.